In addition to the phase plot for differential equations, we do have a mathematical criterion for stability too. And this is called the local stability criterion, which involves the derivative f prime of y. So we have the differential equation y prime equals f of y. We take the right-hand side function, we differentiate, and when this derivative is less than 0, then y hat is actually locally asymptotically stable, which we also call LAS. And if f prime is positive, it is unstable. If f prime at y hat is 0, then the local analysis is inconclusive. It could go either way. How does this relate to what we have learned before? Well, it would be good if we can identify f prime at y hat in our phase plots. Let's look at the phase plots. Let's start from there. So here's the logistic equation again. And let me remind you, so we have the equilibrium points. Y hat is equal to 0 and y hat is equal to 1. In the graph, they're right here, and I make small dots because I want to add some notation there. What is the function f? The right-hand side function f of y is equal to y, 1 minus y. So let's look at the point 0 first, and let's look at the tangent line of the function f at the point 0. What is the slope of the tangent line? Well, the slope is positive. In our phase plot, it's said that the function is actually increasing here because f is positive, decreasing here. So near a positive slope, it seems like we have an unstable situation. Y hat is 0 is unstable, which we know from the phase plot, but also we have f prime at 0 is positive, just from the graph. I will do the calculation just in a second. This is from the graph. If we look near 1, the tangent line looks like this. So we have negative slope, and the point is asymptotically stable. So y hat is 1, is locally asymptotically stable. F prime at 1 seems to be less than 0 just from the graph. So then let's quickly do the calculation. So f prime of y, the general derivative, is 1 minus 2y. And then f prime at 0 is equal to 1, which is positive. Check. And f prime at 1, which is 1 minus 2, which is equal to minus 1, which is clearly negative. Check. So this corresponds to that case, and this corresponds to that case. All right. Here's an example of cross-feeding bacteria. So we say a population of bacteria is cross-feeding if a chemical that is produced by strain A is used by strain B, or vice versa. So let P of t denote the frequency of strain A at a time t, and then a model for P of t was given by the differential equation. P prime equals P times 1 minus P times 1 minus 3P. So now I would like to do the whole shebang. So find all the equilibria, sketch the phase plot, and determine the stability of the equilibria. Then use the local stability criterion, compare the results of 2 and 3, and then explain the biological meaning of all these results. All right, let's try this. Here's the differential equation again. Find all the equilibria. So first we need the function f. So f of p is the right-hand side, and we need to solve f of p hat is equal to 0. So let's do that here. F of p hat is p hat 1 minus p hat 1 minus 3p hat, and this is supposed to be 0. And I'm very lucky because it's in a product form. I can see the zeros right away. So I have p1 hat is 0. I have p2 hat is 1/3. I'm flipping the order of these terms to get it in the right order, and then I have p3 hat is equal to 1. So these are these points, this guy and this guy and this guy. Sketch a phase plot and determine the stability of the equilibria. Well, the function is right here. For phase plot I add my little arrows. That's negative. This guy will be unstable. This is locally asymptotically stable, and this is unstable. So this guy is unstable. This is LAS, and this is unstable. Just from the phase plot. It goes very quickly, doesn't it? And then use a local stability criterion and compare your results with the item in 2. So maybe I just review what we had before. Alright, so for the local stability criterion, we need to differentiate the function f. Okay? So we had f of p is equal to p times 1 minus p times 1 minus 3p. Since we need to differentiate it, I multiply it out. That makes differentiation a bit easier. So then this is p times 1 minus 3p minus p plus 3p square. And then multiplying in the p, then we get p minus 4p square, and then plus 3p to the 3. If this is too quick, stop the video and do it on your own. So then we do the derivative f prime, which is 1 minus 8p plus 9p square. Perfect. And so for the local stability criterion, we need to substitute our equilibrium points into f prime. So if we choose p hat is equal to 0, we look at f prime at 0, which is 1. So 1 is positive, and then we should have unstable. Let's do the next one. So if we have p hat is 1/3, then f prime at 1/3 is, so sub it in, we get 1 minus 8/3 plus 9/9, and this is 2 minus 8/3, which is minus 2/3. And this is negative, so we are locally asymptotically stable. And finally, if we use p hat is equal to 1, then we have f prime at 1, which is 1 minus 8 plus 9, and then this together is something like 2, which is certainly positive, and we are unstable. Alright, so if you compare now, right, so this unstable corresponds to this unstable from the phase plot, this corresponds to that from the phase plot, and this corresponds to this here from the phase plot. Let us try to understand the biological meaning of the results which we just found. Let me remind you that P stands for the fraction of type A bacteria. So meaning P is 0 equals to no type A bacteria, and P is equal to 1 means the whole solution is full of bacteria of type A. To understand the biological meaning, I go back to the time plot, which we have discussed earlier. So in the phase plot, I indicate my arrows going left and right, depending on if f is positive or negative. And then alternatively, we can plot the solutions as functions of time. So p of t as a function of time. And what we do first is to indicate the equilibrium points. So we had 1 at 0, we have 1 at 1/3, and we have 1 at 1. And then if we start at 1/3, I will not change, it's an equilibrium. If I start at 1, I will not change, it's an equilibrium. So what happens in between? So what if we start with an initial condition that is between 1/3 and 1? So let's say we start here. According to the phase plot, we are decreasing. Okay, so we're decreasing, and then we are converging to the level 1/3. If we start here in that region, then f is positive, so we are increasing, and so we also converge to 1/3. And if we are above 1, then the function is actually positive, so we go up here, and we don't need to consider negative values. So this guy here is actually unstable, and you see that the solutions go away. This guy is stable, and solutions converge to 1/3. So meaning, in our solution experiment, if we wait a very long time, we will be in the stable state. So what we will see experimentally is 1/3 type A and 2/3 type B bacteria. Let me summarize. So what is important is the slope. The slope of f at an equilibrium point determines the local stability. This must have been an autocorrect or something. So the slope of f at an equilibrium point determines the local stability. Positive slope means unstable. Negative slope means locally asymptotically stable. The phase plot is a fantastic tool to visualize the local stability criterion.